All right, so this problem is called multiplication game. So Bessie and Mildred are playing a game. They have an integer n, and Bessie has two integers a and b, while Mildred has two integers c and d. The game starts with Bessie playing first, starting with an integer x. On Bessie's turn, she can multiply the current integer by either a or b, while on Mildred's turn, she can multiply the current integer by either c or d. And the first player to exceed the value of n loses the game. So we have function f of x equals 1 if Bessie wins the game starting at an integer x, and f of x equals to 0 if Mildred wins the game starting at integer x. And we assume that both players play optimally. So we want to find the sum of the function f of I for all I from I to n. I equals 1 to I equals n. And this is essentially just summing the games where Bessie would win. Great, so let's look at the sample input over here. We have, oh, okay, we have n equals 2000 and a equals 40, b equals 50, c equals 40, and d equals 50. Right, so on any number between 2 and 50, Bessie can multiply the number by either a or b and force Mildred to lose on the next turn. So for example, if x equals to 2, Bessie can multiply by 50, where 2 times 50 equals 1000. And as you can see, anything that Mildred does on her next turn would exceed 2000 and lose her the game. Now, if x was 50, Bessie could do 50 times 40 equals 2000. Now, if you notice, this does not actually exceed 2000. It is exactly equal to 2000. So Bessie does not yet lose the game and would force Mildred to lose on her next turn. Now, if x was equal to 1, or let's say if x is greater than 50, then anything that Bessie does would exceed 2000 and would lose her the game. So if x was 51, then 51 times 40 would be 2040, which exceeds 2000 and would lose her the game. Now, if x was equal to 1, then Bessie could play anything. She could do either multiply by 40 or multiply by 50. And in both cases, Mildred would have an option to not lose. So in this case, she could multiply both by 40. And in both of these options, Mildred would not lose on her turn and would in fact force Bessie to lose on her next turn. So the actual answer for this sample input would be 50 minus 2 plus 1. So all the numbers in the range between 2 and 50, which is 49, as you can see from the sample output. Okay. Now, for this problem, we can consider a DP array of I and either 0 or 1. DP of I of 0 would mean it is currently Bessie's turn, and x is equal to I. And alternatively, DP of I1 would equal to Mildred's turn. Where x is equal to I. And on this, for both of these, the DP array equals to 1 means that Bessie can win. And if DPI of 1 is equal to 1, then that means Mildred can win. And 0 means the other way around, where for the first one, Bessie would lose, and for the second one, Mildred would lose. Okay, so for any player J, if it's J's turn, then J can win if they can force the other player to lose. Otherwise, J would lose. So then we would have the following transition. Here, dp of I 0 is equal to 1 if I is greater than or equal to n, which means that the player already exceeded the number on their last turn. And it would equal to 1 if the min of dp of I times a 1, or the dp of I times b 1 is equal to 0. So this would mean that if either of these solutions, picking multiplying by a or b, could force the other player to win, then Bessie can win currently. And if neither of these are true, then Bessie is sure to lose on uh, on this number. Okay, and the same thing, it's the same thing for dp of I of 1, with just the other way around. And this would be O of n, right? But if you look at this, n is 10 to the 11th, so we can't actually do this, and this would exceed time limit. So this will pass the first two subtasks, since n is less than 10 to the 7th. But if you look at the third subtask, it will not actually pass. So there are multiple ways that we can try to do the final subtask. We can try to either optimize the DP without, yeah, we can try to optimize the DP. Oh, it's not clearing. Okay, so without loss of generality, we can assume that A is less than or equal to B, and C is less than or equal to D. This just means that A and C are the smaller of the two numbers. Then we can notice that Bessie will lose if she starts from anywhere between the ceiling, or no, this is a bracket, and the ceiling of n plus 1 over A and n. So anywhere between these two numbers, Bessie would lose. And anywhere between n plus 1 over C, n, Mildred would lose. This motivates that the dp that was defined earlier is constant for many intervals, like the ones that I defined over here, which leads to the following solution. Okay, so we have an x0 equals y0 equals n plus 1. For I starting from 1, yeah, if I is odd, I mod 2 equals 1, then our xi would equal to the ceiling of y of I minus 1 divided by a. And of what y of I, sorry, would equal to x of I minus 1 over c. And for all of these, from xi from the range of xi to xi minus 1 minus 1, Bessie would lose. Great. Similarly, if I is even, so I mod 2 is equal to 0, then we could have x of I, or xi is equal to yi minus 1 divided by b, and yi is equal to xi minus 1 divided by d. And similarly, xi to x, y, I minus 1 would mean that Mildred loses. Okay, and to visualize this even more, I can draw two bars of length n. Right, this is for Bessie, and this is for Mildred. For all of these, this interval over here, which is, this is uh, x of 1, which is also the ceiling of n plus 1 over a, Bessie would lose. And similarly, in this interval over here, or this is this interval of a different size possibly, this is y of 1, which is n plus 1 over c. For all of this interval, Mildred would lose. Now okay, my pen is not changing color. Right, so for the next interval, Bessie would win. This is between x1 and x2. And x2 is y1 over b. And this similarly is the same for Mildred. Mildred would win for all of y2 to y1. And this is between x1 over d. And you do this so on, and you can find that this would actually work to find the answer for all, for any n up to 10 to the 11th. Great, and that is how you do the problem. Oh yeah, the time complexity for this would be the log of the minimum of A, B, C, and D of n. Of n, which, as you can see, is much better than the O of n for an n equals to 10 to the 11th from before.